Alright, today is going to be the introduction into truss design, what it is, and what exactly it means. Now, like I said in the description of the possibilities, truss design is something that pretty much every single student who is going into physics or engineering is probably going to have to deal with. Now, first thing, let's start with what a truss is. Now, a truss is a framework used to support some load. Okay, now most of the time you are going to see trusses on bridges. It is not always going to be there, but most of the time it will be. Sometimes the truss support for bridges could be above the bridge. Sometimes they could be below the bridge. Right? It really depends on the bridge itself. And sometimes there will actually be no trussing whatsoever. Right? The key thing here is a framework. Some of the older style bridges are going to, instead of having this general type of a shape to it, or whatever else you may have. There are several different types of trusses, but instead of having this as either a structure above the road deck or below the road deck, instead you may just see a very long, solid steel beam that goes underneath the entire bridge surface. Okay? Now, this would be trussed, this would be non-trussed. The reason that we have gone more with trusses on most newer bridges is due to the fact that, well, less metal is cheaper than more metal. To have a big, wide piece of metal being used the entire span of a bridge is not economically feasible for many long bridges. It's a lot cheaper to use long I-beams instead and use it as a ribbed structure instead of a vert structure. Alright, now the other place that you're going to commonly see these now are with roof support. Alright, unless you have basically an open raftered roof, you will probably see inside the attic is going to be a number of things like this. Okay, now basically the old school way of supporting a roof would have been to put large posts in the center, and off of those large posts putting single beams that went down and out. Now, although this is very functional, if you get a heavy snowstorm, anything that's going to put excess stress, is particularly on the middle of each of these boards, would cause the entire roof to collapse. By using a truss structure, you're able to, yes, it does take a little bit more material, but the entire support itself is much more, well, worthwhile, much more strong. Okay? Now, general shapes. The big thing that you're going to notice with most trusses is that they are going to be, in general, a series of triangles, one after the other. Now, the way that I normally simulate why they would want to use a triangle is consider having yourself a pile of popsicle sticks. And the only way that you can connect those popsicle sticks to each other was by driving a nail through one end into the other. Okay? If each one of these was a popsicle stick, we had one nail pinching these, one nail pinching these, and one nail pinching these, this structure would be upright. If you applied a force this way, it still will be able to resist. If you apply a force this way, it still will be able to resist. If you apply a force this way, it'd still be able to resist, and it will maintain its same shape. Okay? If you tried to think about the same exact thing with a box or a square with one pin in each corner, well, think about what would happen. If you pushed right here, the entire shape would change. If you push right here, the entire shape would change. If you push here, the entire shape would change. Same exact thing here. Now, what you're going to notice is these things are going to be series of triangles. A triangle is a relatively strong shape, and, well, it's just much more useful in these things. Now, I'm going to introduce the math, but I'm not going to go into the math yet. All right. Today is just going to be a very general, generic, basic overview of what's going on. Tomorrow is going to be an introduction into the pieces that are holding it together. And then Friday we will actually start into the math. Okay. But this entire thing is built off of the premise that it is a static structure. Now remember what static means from static electricity, from coefficient of static friction. Static means stationary. And if you're really thinking about things, you probably want your bridge that you're designing to be stationary. You probably want the roof that you're designing to be stationary. So, considering that it is stationary, that means that we have two different situations that are going on. But the big overall concept is that this entire thing is in equilibrium. Okay? In order for it to be stationary, that means that it cannot be moving. If it is not moving, that means two different things are going on here. The sum of the forces that are acting on that structure are going to be equal to 0. This is going to be one of the key equations that you're going to be using. All right. Now, this is going to be broken down into two different dimensions. Just like we've done this in the past, you're going to have the sum of the forces in the y direction have to all come together to equal 0, and also the sum of the forces in the x direction are going to have to come around to equal 0. Okay? Now, the second thing that is going to be important is we've used this in the past, but I'm going to use it under the new terms now and relate it to the old terms. All right? Most engineering courses are going to call this the moment or the moment of inertia. The moment of inertia of an object basically tells you how much it is going to want to rotate due to outside forces on the object. So in other words, this is the same exact thing that we did with torque last year. Now, just like you don't want the thing to be accelerating up and down or accelerating left and right, you also don't want it to twist. So that means that the sum of the moments is going to have to also equal 0. All right? Now, the difference here. This part over here is absolute. Right? No ifs, ands, or buts about it, and no matter what reference frame you choose, the y direction is always up and down. The sum of the forces in the y direction always have to equal 0. X direction is always left and right. The sum of the forces in the x direction always have to equal 0. The thing with moment of inertia is moment of inertia, the start point is arbitrary. In other words, you are going to be able to pick the point around which this is going to rotate. Now, by doing that, you can eliminate a lot of unknowns, and you can work your way through a lot of different situations using it. Okay? I will explain how this is used momentarily. All right? But these are the two biggest things that you're going to be dealing with. The key thing is, every single time, it is always going to equal 0. The fact that it equals 0 tells you that this is the static case. All right. Now, let's look at a very, very, very basic structure. Actually, you know what? Let me go into the connecting points first. After I go through the connecting points, then we'll go into a basic structure. All right. So, methods of connection. Now, there are going to be several different ways that things can be connected together. All right. Now, depending on how an object is connected together, that's going to change what types of forces are acting on that object. Now, I want to get the book out in front of me so I can take some screenshots and put those on the screen. So give me a moment while I get that organized. All right, the methods of connection are just the different ways that two objects can be tied together. Now, the way that these objects are tied together is going to determine exactly what types of forces are going to be acting on it. Okay, some of these are going to be reviewed from previous year or from last year. Some of this stuff is going to be brand new. Most of this stuff we are not going to use. I am just going to talk about the most common situations here. Okay, so let us start with the basics of the basics. Okay, now this is, and also do not worry about copying down exactly what this is. I should have a copy of this to you, I'm hoping by Friday. It may be a little bit later, depending on how quick I can get down to the copy machine. But, right, with these, right, if you've got a cable, now remember from last year, a cable, a rope, a chain can only pull in the direction of that cable, rope, or chain. So when you're pulling with a cable, rope, or chain, there's only one unknown force associated with that cable, rope, or chain. That cable cannot cause a rotation around that point. It can only simply push with a force. Now, this one down here, let me focus that a little bit better so you can actually see. This says smooth surface support right here. But a smooth surface support means that the only thing that can happen is a normal force pushing directly up through the bottom of that truss structure. So in other words, once again, we just have a single force that is acting straight up. That is the only way that this can interact. Right? A little bit more often than seeing a smooth surface support, you're going to see a situation such as a roller. Now with a roller, it's going to be the same exact thing. This roller cannot resist any forces going forward or backward. It is going to simply roll. But the only thing it can resist a force is going straight up and down. Now, I understand this is probably going to cause you guys a little bit of confusion. That's why I'm introducing it today before we will actually have a live lesson tomorrow. Okay? Now, a couple of these are going to be more commonly seen than others. Alright, the top two are probably going to be cables and rollers. These other ones are also methods of connecting. Right? Now this is what's called a ball and socket. Right? In a ball and socket, that means that you've got kind of like one of those old school pen holders you might have seen at a bank, where you can set the pen inside the pen holder, and that pen holder can point in any given direction. Now, notice that this ball and socket can rotate freely, so because of that, it cannot hold any moments of inertia. All it can only hold is individual forces. The difference here is, though, that in a ball and socket, it can apply a force in the Y direction, and it can also apply a force in the Z direction. It can also apply a force in the X direction. It can resist forces in all three directions because this bottom post is stationary. Now, these are journal bearings. We're not going to worry about these. The difference between this and the ones that we've done up here is that if I were to try to apply a force to this bar to twist it in this direction here, this would obviously eliminate my possibility of being able to do that. So in other words, instead of just supplying forces up and down and front and back here, because obviously it cannot supply a force down the length of the shaft. If I were to push right here on this end of the shaft, it would slide right through this journal bearing. But it can apply a force in this direction, it can apply a force in this direction, and it can reduce twist in 2 dimensions. Single journal bearing with a squared shaft, you're barely ever going to see that. In all of my years dealing with this in college, I think I've dealt with a math problem with that maybe once. Alright, now the remainder of them here. Thrust bearings, once again, still very, very uncommon. Single smooth pin. This is going